Hello guys, welcome to this video. In this video, I want to discuss an interesting question or I just want to share my opinions about the future of physics, more specifically the future of theoretical physics. A lot of people have asked me, and I've made a lot of comments on this topic in my writings, in some of my previous videos, maybe in my book, in my articles, in some of my LinkedIn posts, maybe also, and also personally, to the people who know me, I've made a lot of comments about this. So a lot of people have asked me this question, and not just because of that, because this is an important question to address in any case, even if regardless of whether I have been uh, asked or not. So the basic question which I'll be addressing in this video is that, what is the future of theoretical physics? My views on the subject, and what role will mathematics play in it? Of course, we have this notion that physics and mathematics are inseparable. In physics means mathematics. Without mathematics, there is no physics, and all of that is true. But when I say mathematics, the future of physics, that is not exactly what I mean. I'm not talking about mathematics as a tool to solve problems in physics. That we have been doing for the past centuries, for the past in the past, that is what we have been doing. We have been using mathematical techniques and mathematical tools to solve problems in physics. So in that case, in that sense, mathematics has played an important role in the past of physics as well. But when I say whether mathematics is the future of physics, that is not exactly what I mean. So then you may ask that what is it that I mean? I think the answer will be clear to you as we proceed. So it's just a short slide, Google Slides, a short 10-page presentation I have prepared. Which I'll just roughly discuss briefly discuss in this video. So we start with this question: mathematics, the future of physics. Right now, it's a question, and that is the question which we will address in this video. Like, is mathematics the future of physics? And what do I mean by that? That is also I'll discuss. That will also be revealed as we continue our discussion. So in this short presentation, I will briefly discuss my views about the future of theoretical physics and the future of science more broadly, in a non-technical fashion. Now, before we even start, I strongly emphasize that all of this is mostly speculative at this stage. However, of course, I have outlined my reasoning behind my claims as clearly as possible. It's not like I'm not narrating any fairy tale or anything. But yeah, I'd love to. But yeah, just to clarify, this is most of this is speculation. None of this is verified. And if by verified you think, you if by verified you understand experimentally verified, then of course none of this is verified. But yeah, I'd love to know your thoughts about this. So please do comment below after you watch the video. I don't care whether you are an expert on the topic, whether you are a theoretical physicist yourself, or you're just an ordinary person, just a person curious about physics. I don't care. I would love to know your thoughts about this. And yeah, even criticisms are welcome, as long as they're constructive criticisms, as long as they're valid points and not done for. As long as it's criticism for this, not criticism for the sake of criticism. I hope you understand, right? Anyway, so if you think about it, working on theoretical physics today is more likely to provide you with new insights in abstract mathematics than any insight about the physical world. Like long back, physics was the study of the physical world. Even today it technically is, but long back, if you're working on physics, that means even if you're working in some lab, or if you're just simply observing the world around you, the changes taking place in the world around you, the way the bodies move, the way things behave, or if you're carrying out some experiment and you're trying to understand, trying to build some theory that will explain the results of the experiments, uh, mm, and that kind of thing. But today, for the last couple of years, if you think about it, theoretical physics, if you choose to work on theoretical physics only and not experimental physics or anything, then it's more likely that you will arrive at some new insights in abstract mathematics. Maybe say you will say you find a proof of some long forgotten mathematical theory or something like that. Even if you're working on theoretical physics for say many years, and but it's very unlikely that you will arrive at any verifiable or any conclusive insight about the physical world, any significantly new insight about the physical world. That's why you see the state of theoretical physics. There has not been much significantly I mean, there has not been any significant progress for the last almost the last 5 to 6 decades, if you think about it. Once I mean The standard model is the last theory in physics which has been kind of verified experimentally, and after that there has been no fundamental shift in our understanding. I mean, if you think about it, during the early 20th century and little before, physics was going through a transformative phase, and that was the era of that was kind of the golden era of physics. I mean, Einstein proposed his revolutionary theory of gravity, and then on the other hand, quantum development in quantum mechanics was going on. Niels Bohr proposed his Niels Bohr explained atomic spectra and then proposed his atomic model, and then de Broglie put forward his wave particle the duality, his de Broglie hypothesis. And then yeah, by 1927 I guess we already had the Schrodinger's equation, the which described the time evolution of any quantum particle. And yeah, not just the Schrodinger equation. We had, all of physics was going through a very rapid progress, be it relativity in the field of relativity or astrophysics. I mean, general relativity, or in the field of quantum mechanics. And then very soon we were ushered into the era of nuclear physics, and then quantum field theory, and grand unified theories, standard model, and all of this stuff. And on the other hand, progress in astrophysics was also going on at a at a rapid pace. But then say, for the last few decades, if you see, progress in the applied physics and in the experimental techniques we use in the computational methods, computational physics, experimental physics, artificial intelligence, machine learning, in all of these areas progress is going on. The progress is really impressive. But progress in theoretical physics, progress in understanding the fundamental laws of the universe, beyond particle physics, beyond the standard model, and beyond general relativity, what progress in this area, it has been really disheartening. There have been new hypotheses, new proposals, like string theory, loop quantum gravity, even more lesser known ones. And occasionally we hear of some we read some articles and stuff like, finally are we close to a theory of everything. Then some physicists propose that gravity is entropic, or is then some physicists propose some his own version of a theory of everything, and all of these things. Some of them are really interesting and worth taking notice, but most of them are kind of clickbait. So yeah, there has been no significant progress. And why I say no significant progress, because even though I believe some of these ideas like string theory and all, they have a lot of potential, and they're not ideas that should be thrown in the dustbin, but these ideas have not been verified experimentally, and I don't think they will be verified experimentally anytime soon. So that's the problem. Uh, so yeah, it can no longer be said that theory and experiment go hand in hand like it was during the early 20th century. You understand? So this has led many prominent physicists to the conclusion that physics is currently lost in math. I mean, just a second. Yeah. Okay. So like I told you, in the during the early 20th century, like theory and experiment went hand in hand. Some experiment was carried out, and some theory was verified. For instance, Robert's Millikan algebra experiment verified. That was how the charge of the electron was determined. Then there were a lot of experiments which verified known theories. Some experiments which showed us problems with the classical theories like black body radiation, and which paved the way for new theories. Theory and experiment went hand in hand. That was the case during the early 20th century. But right now that is not the state. That is not the case. So this has led many prominent physicists to the conclusion that physics is currently lost in mathematics, and we should take physics back to its empirical roots. Physicist Sabine Hosenfelder, she actually wrote a book on this topic, and the name of the book is Lost in Math. It's a very good book. You can check it out, and she has she has just uh, outlined her arguments about why she thinks that physics is currently lost in mathematics. And she has kind of explained both the schools of thoughts, both the sides. But anyway, it's a good book to check out. I myself am reading I myself started reading the book a few months back, but I first then one thing due to one thing and another, I couldn't finish the book. It's kind of I just read half of it, and it's then I didn't get the time to finish it. So I will not make any statement about the book, but yeah, you can definitely check it out. That's for sure. Now, so some physicists are saying that we are currently lost in mathematics, and these new theories, or like string theory and all in theoretical physics, these theories are, they have no experimental validation at all. They are just based on mathematics and mathematical intuition or mathematical elegance. But according to some physicists, that they argue that, and they worry that this means this is taking us farther from the physical world, farther from the real world. We are currently getting lost in mathematics, and we should take physics back to its empirical roots. We should again focus fully on experiments. Yeah, maybe experiments cannot reveal the fundamental nature of the universe. I mean, our experimental methods are not that advanced yet, have not reached that level yet. But they're saying that most of these theories are just speculation, and most of them are to be thrown in the dustbin. I mean, that's what they're saying in very simple terms. However, I believe it's not always a bad thing if exploring physics takes us to the land of mathematics, because mathematics is undoubtedly the most fundamental level of understanding that we know of. I mean, mathematical insights might find their use in some physical theory sooner or later. Suppose today you are supposed research, you are conducting some research in theoretical physics, and you arrive at some mathematical insight, and you might think like that. I mean, there is no apparent relation between this mathematical insight or mathematical theorem and anything in the physical world. So you might think like, oh, maybe it was fun to work on this mathematical theorem, but this is not actually physics. I'm no longer doing physics. I mean, this is not this will not be of any help in understanding the real world. But you never know whether this mathematical theorem or mathematical insight, whether this will not be used. I mean, whether or not this will be used in the future to explain to some unknown aspect of the physical world. I mean, that's why, see, mathematical insights might find their use in some physical theory sooner or later. Because mathematics has it all, and studying mathematics could be a shortcut to understanding the fundamental structure of the physical universe without having to rely on any messy experimental methods or data. I mean, of course, while experiments are inevitably, they are extremely important, they play a crucial role in filtering out what is possible and what actually happens in our world. I mean, science is not science without experiment. I mean, even the very scientific method, that is how we define the scientific method, that a hypothesis is a scientific hypothesis only if it is falsifiable. I mean, if it could have been proven wrong, but it turned out to be true. And because without experiments, you cannot say whether it's true in our world. So, of course, I'm not saying experiments are not important, but sometimes, I mean, at least presently, you see, theoretical physics has advanced so far that experiment is not being able to catch up. I mean, we are not being able to devise an experiments that will verify the present theories in theoretical physics, like string theory and loop quantum gravity. I mean, that does not mean such experiments do not exist. But whether such experiments are feasible is another question. And like I said, but in some situations, mathematics could be a shortcut to understanding the fundamental structure of the physical universe. I mean, and if we just do use mathematical intuition to understand the structure of the universe, of course, some people might argue that it is not on solid experimental ground. It is not verified experimentally. But yeah, the beauty or the benefit of this approach is that you do not have to rely on any experimental methods or data, and that means you kind of take care of a lot of issues like errors and all, statistical errors, and then a lot of kind of issues which can arise. I mean, of course experiments are important, but after a certain point, maybe mathematics alone can do the trick. I mean, that's what I think anyway. Mathematics alone can do the job. And why am I saying this? Although this might sound very controversial, that I'll explain in the next few slides. So the unreasonable effectiveness of mathematics. Now, a lot of people, a lot of physicists, including, I mean, this term, the unreasonable effectiveness of mathematics, this term was actually coined by Eugene Wigner. He was a physicist who, I mean, because why did he say the unreasonable effectiveness of mathematics? Because, I mean, I think nobody will doubt, nobody will object to the statement that mathematics has been really effective in explaining the physical world. All of physics is based on some mathematical framework. We use mathematical tools in physics all the time. So mathematics is an effective tool to understand the physical world. That's no doubt. But why is this unreasonable? Because mathematics was developed long back, centuries back, without any application in mind. I mean, those people who were developing the concepts of mathematics, like group theory and vector spaces, matrix and everything, linear algebra and all. I mean, at the very primitive level. I mean, I'm talking about hundreds and hundreds of years back. I mean, they were not developing these mathematics because they knew that I mean, they were not developing this mathematics with some specific application in explaining the physical world. They did not have any application in mind. They were just developing mathematics because they were interested in logic, in mathematical logic. But many years later, we found that exactly these mathematical concepts they do a beautiful job in explaining the physical world. They do a beautiful job in forming the framework in which we can define our physical theories. And that is, if you think about it, this is a bit unreasonable, this is a bit kind of counterintuitive, and this is a bit surprising. Like, how come the mathematics that has been developed so many years back without these applications in mind, how come almost all of these mathematics find some application in some areas of physics or the other? So when linear algebra and the concepts of vector spaces, matrices, were etc. were developed so many years back, nobody at that time could think of any direct applications of these ideas in explaining the physical world. I mean, of course, these people discovered this. I mean, at the very basic level, all of these concepts were developed. Like the basic aim was to develop an approach to solve a system of linear equations. But that was done because we can model a lot of things which we see in real life as linear equations. I mean, a lot of real life problems. I mean, not problems about physics or about the fundamental nature of the universe, but like the problems we used to do back in high school, right? Like a lot of problems, simple real life problems can be. I mean, a lot of real life problems can be simplified if you can express them or model them as a set of linear equations. And from the different approaches of solving linear equations, slowly all of these mathematical concepts were developed, like linear algebra, vector space, matrices, and even vector spaces. Now, I don't consider solving a set of linear equations for a real life problem like the ones we used to do back in high school to be an application in understand the physical world. I mean, that's why I said that nobody at that time, when these concepts were being developed, nobody at the time could think of any direct applications of these ideas in explaining the physical world. But now we know that the entire formulation of quantum mechanics is based on a certain type of vector space, and eigenvalues and matrices offer us a well-defined mathematical way of predicting the possibilities and probabilities corresponding to measurements we make on a system in quantum mechanics. Beyond that, quantum mechanics has led us to quantum field theory and the standard model of particle physics, where to explain the interactions between the fundamental particles or the elementary particles, we make extensive use of the mathematics of group theory, symmetric groups, which was again developed many years back without any application in mind. Then in Einstein's general theory of relativity, we make use of tensors and all of this, matrix and all. I mean, all of this is a bit technical. Some terms you may not understand if you are not formally trained in physics. But the point I'm trying to make is that mathematics, a lot of mathematical ideas which were developed many years back without any physical application in mind, without any application in physics in mind, all of them find use in some physical theory or other. That is what I want to highlight in this particular slide, right? And not just use. I mean, our entire theories of physics are based on this mathematical structure, these mathematical theories, right? So all of this is suggestive of the fact that probably everything in the physical world has a mathematical description. Now, when I was back in high school, I used to think that Max Tegmark was crazy for suggesting his mathematical universe hypothesis. Max Tegmark is a physicist who thinks that the universe, he has a hypothesis called the mathematical universe hypothesis. I mean, you can read his book called Our Mathematical Universe. He has written a book which is titled Our Mathematical Universe. It's a very interesting book. You can check it out. The first few chapters are on cosmology and all, but in the last portion of the book, he illustrates his hypothesis in a very good way, and I think you might enjoy the book. I mean, if you're watching the video and if you're interested in the topic that is being addressed in this video, then definitely will enjoy the book. So it's one thing to say that the universe is described by mathematics, but what does this guy mean when he claims that the universe is mathematics? I mean, that is what he claims, that the universe is not only described by mathematics, but the universe is actually a mathematical structure. The universe actually is mathematics. So yeah, when long back, even this idea seemed crazy to me, but now, at least to me now, it seems to me that this idea might in fact be correct. In context of Platonism, I don't think mathematics is invented by humans. I think we are only discovering the mathematical truths. Just give me a second. Uh, yeah, so where was I? Okay. So, but yeah, in the context of Platonism, so what is Platonism? Platonism is basically, roughly speaking, I don't remember the exact way it was stated, but it's roughly speaking, the idea is that the mathematical structures and mathematical objects, or I mean, which we call abstract objects. I mean, which cannot be, which are not physical. I mean, which cannot be seen or touched or felt physically. Uh, like for instance, the mathematical concept of a number. Say the number two. Now, what is the number 2? I mean, if I tell you that define 2, how will you define 2? 1 plus 1? Okay, fine. Then how will you define 1? I'm not looking for the mathematical definition of 2, but how do you define a number? You cannot show me 2, like you cannot show me uh, say two mobile phones and say that this is the number 2. That is a manifestation of the number 2. Like, yeah, if I have two of these, if I have two identical objects, then I mean, if I have one identical object and then another of the same identical object side by side, then I can say that we have two such object. But that is not that is not, you're not really defining two. And if you think about it for some time, that there is actually, we don't know of any way of defining 2, because 2 is an abstract mathematical entity, it's a number, and it has no physical existence. You cannot touch 2, you cannot see 2. You can see two mobile phones, you can see two laptops, you can see two human beings, you can see two stars in the sky, whatever, but you cannot see the number 2, because it has no physical existence. Now, according to Platonism, all of these mathematical ideas, mathematical concepts, mathematical forms, or mathematical entities, mathematical structures, all of them actually have an existence. I mean, even if we do not see them, but I mean, eternal. I guess Plato used the term eternal reality, and basically he said that beyond our physical world, there is a mathematical world which we cannot, maybe we cannot access, but it is kind of it does not change. I mean, there is no change at this level. In the physical world, everything is changing in the world around us, but in the mathematical world, beyond our physical world, all of these mathematical structures and entities, they exist even if we cannot see them or touch them or feel them, and this world is not changing. That is the kind of Platonism, like the existence of a higher reality. Of course, you might think that this is kind of fairy tale. Why suddenly should I start believing that such a world exists? But I'll tell you why. Because if mathematics was just a human invention, then, like I said, the unreasonable effectiveness of mathematics, then it's unlikely. How is mathematics so effective in describing everything in the universe? So maybe mathematics is not invented by humans. Maybe we are only discovering the mathematical truths, but these mathematical truths, they have always been there and will always be there, regardless of whether the physical universe exists or not. Because the universe is physical, so it is changing, and of course, certain changes can come about which will maybe destroy the universe. I mean, after trillions of years, the universe will be destroyed because of, the law of thermodynamics, like the heat death of the universe. I mean, there are a lot of theories about the fate of the universe. If you read cosmology, like the critical density, whether the universe will continue expanding or whether it will kind of reach a maximum, I mean, static state, but whatever, this heat death. But the point is that the universe is changing, and that means it's possible for the universe to come into existence and to be destroyed as well. So it's not eternal, it's not permanent. Okay, so as I was saying, like I don't think mathematics is invented by humans. I think we're only discovering the mathematical truths, but they have always been there and will always be there, regardless of whether the physical universe exists at all. Because like I said, the physical universe is it's full of changes, and changes are possible that will destroy it. And I mean, it was not there forever. For instance, most likely, if you go by the Big Bang theory, anyway, it's changing, and it's certainly possible that the physical universe will no longer exist after trillions of years. Because all of these predictions, they are based on theories of physics, and since it's a physical universe, it has a lot of constraints, but no such constraint exists on this mathematical, on this space or level of mathematical truths, because nothing is changing at that level. It's just eternal mathematical structures and objects. I mean, you cannot destroy the number 2. You can destroy, you cannot even you cannot destroy information, even in quantum mechanics. Even in modern quantum information theory and all, you cannot really destroy. Suppose if I give you two objects. Suppose if you destroy the object, you cannot obviously destroy the quantum information associated with the atoms or molecules or electrons that make up the object. But yeah, at our level, if you say burn the objects or somehow destroy them, then do you really destroy the number 2? Do you really destroy 2? No. If you destroy two objects, you do not destroy two. In fact, there is no way of destroying two. Now the question is, some people will say that if there were no human beings or no consciousness to perceive this notion of two, then two will be destroyed. And those people, I mean, that school of thought does not believe in Platonism. But the other school of thought, which believes in Platonism, and recently I think I am more into this group, they say that no, even if there was no consciousness to think about two or to perceive the notion of two, as a mathematical structure, all numbers, including the number 2 and all mathematical structures, they will always exist, because they are not, because mathematics is not invented, they are not dependent on us. I mean, we did not invent them, they have always been there even before we came into existence. I mean, that's what might be the case anyway. That's what some of us believe. So the universe, I believe, is a manifestation of some subspace of the most general mathematical space possible, and everything in the universe probably has a unique counterpart in this mathematical subspace. Now, when I say space, from the point of view of physics, space is something like space might remind you of distance, like I am in three-dimensional space. But when I'm talking about mathematical space, I'm not really referring to any physical distance or anything. It's a for instance, it could be a vector space, a tensor product space. These are all examples of mathematical spaces. A mathematical space is, in simple words, it's a collection of mathematical objects or mathematical entities. That could be, vectors or whatever, vectors, scalars, whatever. And these entities follow certain mathematical rules, which are, I mean, they're just general rules, they do not change. I mean, that is how we define a mathematical space. And it might seem like, oh, that's a simple definition, so what is so special about spaces? Just a collection of elements, mathematical elements which are following some rules. But you'd be surprised to know that mathematical spaces are very interesting, and studying mathematical spaces reveal a lot about the physical world as well. That's why I think it's likely that the universe, I mean the physical universe, is probably a manifestation of some subspace. First of all, the most general mathematical space possible. That means I'm essentially talking about all of mathematics. That is all that is possible. All that is possible. That is what I mean by the most general mathematical space. A space containing all mathematical entities, all possible mathematical structures, everything. Now, then what is the subspace of the most general mathematical space? That means I'm kind of putting constraints, and now I'm only dealing with a subspace. That is only a small portion of this mathematical space. But to form a subspace, you cannot just take, just suppose in the original space there are 10 elements. I mean, just an illustration. The most general mathematical space is will of course contain an infinite number of elements. But let's say we have a space of 10 elements, and if I take any, say, 3 or 4 elements out of these 10 elements, then is it a subspace of that space? No. If I say I have a set of 10 elements, and if I take 3 elements from this from these 10 elements, then that 3 elements form a subset of this bigger set. True, because how do we define a set? A set is just a collection of elements. There is no these elements need not follow any relation between them. I mean, that is not required to define a set. But when you're defining a vector space or any space, inner product space, tensor product space, I mean any mathematical space, that means I mean, it's not just the mathematical entities, it's not just the objects which constitute the space. You need to also take care that all the rules of the space are being satisfied by all the objects. So if you take a particular group of elements from this general mathematical space, then you also need to make sure that these smaller group of elements, they also follow the same rules of the space. Only then you can say that it's a subspace. And I believe the physical universe is a manifestation of this subspace. What do I mean by manifestation? Because it's likely, as we will discuss in the next slide probably, yeah, in the next slide, it's likely that this subspace is, I mean, it's a subspace of the most fundamental mathematical space, but it is still a mathematical space, right? It's not the most general mathematical space, but it is still a mathematical space. And I believe that, this, since it's a mathematical space, it's more fundamental than our physical universe, than our physical level of understanding. So it will probably not contain all the concepts which we are familiar with or which we use to describe the universe. That's why I say the universe is not this mathematical subspace itself. Rather, it's a manifestation of this subspace. The universe emerges from this subspace. I mean, we have the most general mathematical space, and we are just using certain constraints, maybe the laws of physics or something, to filter out only the most general mathematical space means all the possibilities. I mean, all that is possible. But physics only cares about what actually happens in the physical world, in the real world, right? Mathematics cares about every possibility, but physics will only care about those possibilities that take place in the real world. So all possibilities correspond to this most general mathematical space, and from this we are filtering out only those possibilities that takes place in the physical world. I mean, only we are kind of filtering out physics from mathematics, and that is the subspace. But now to build the physical world around us, we take some kind of manifestation of this subspace. I mean, that is what I believe, and that's my idea. But like I said even in the beginning of the video, that all of this is speculative, and although I have plans to work on these ideas, a lot of physicists are already working on these ideas, but right now we do not know exactly how to explain the manifestation or the emergence of the physical world from a mathematical subspace, or whether this idea is correct at all, right? uh, but yeah, I believe that everything in the universe probably has a unique counterpart in this subspace. I mean, that's why I'm saying that the universe emerges from this subspace. Everything in the universe, it can be mapped to something in the subspace. I mean, this subspace is essentially a complete description of the universe at a different level, at a more mathematical level. And the best we can hope for is that if this correspondence between the physical elements of the universe and the mathematical elements of this corresponding subspace, if this correspondence is one to one, I mean, that means if to each physical phenomena or physical object in the physical universe we can uniquely associate a unique element of this mathematical subspace, I mean, that would be the best, because that would make our understanding, I mean, that would make our research in theoretical physics, and that would make our quest to understand the fundamental structure of the universe a lot easier, right? But yeah, in conclusion, as I already said, I think every physical phenomena must have a mathematical description, and once we find the mathematics behind all physical phenomena, we probably will be able to better appreciate the fundamental structure of the universe. And yeah, using this, we probably can formulate a true theory of everything. Now, let's discuss the specific point where I think mathematics can directly help physics, and that is the explaining the emergence of space-time. Now, in physics, as I discussed in some of my previous videos and writings, so I will not go deep into this here. I will assume you know this, and if you don't, you can always check out the internet, or I mean, whatever. There are a lot of resources. But yeah, for the purpose of this video, I think it's enough to know that right now in physics we have two major fundamental theories. One is general theory of relativity, and the other is quantum field theory. And both of these theories work in their domains of applicability. Both of these theories have been experimentally verified, and they work to those areas for which they have been built. I mean, we cannot say that one is correct and the other is incorrect. But here's the problem, that both of these theories work with fundamentally incompatible descriptions of space-time. I mean, in simpler terms, both of these theories treat space-time differently. I mean, general relativity describes space-time in such a way that is in disagreement with the way quantum field theory describes space-time, or vice versa. So because of this, a lot of physicists speculate that space-time is not fundamental, because if two successful theories, I mean successful at our level, so anyway, if two successful theories can have fundamentally different descriptions of space-time, or fundamentally incompatible descriptions of space-time, that means probably space-time is not the most fundamental level of understanding that we can achieve. Probably there is a deeper level of understanding, at that level both of these theories do not disagree. Both of these theories can be reconciled at that level. I mean, the basic idea is this, that space-time is emergent from a deeper level of reality. I mean, not reality, from a deeper level of understanding. And this deeper level of understanding, let's call this space-time X, kind of. I mean, just a fun stuff. Okay, no. I mean, there is no official any term like this. So then, although both of these theories, both of these successful fundamental theories, general relativity and quantum field theory, although both of these theories do not agree on the description of space-time, both of them must agree on the description of space-time X. I mean, that is how we define this deeper level of understanding, space-time X, right? That is the idea. So space-time is emergent from space-time X. That is the idea. So yeah, because of this, a lot of physicists speculate that space-time is not fundamental, that rather it's emergent from a deeper level of understanding. Now, I think it's possible that this deeper level has no physical description at all. What do I mean by physical description? That means it can be described using physical concepts like distance and time. But it's possible that this deeper level which we're talking about, it has no physical description, because it cannot contain within it the notions of space and time. See, we are trying to explain the emergence of space-time. So, since space-time is emergent from this level, then this level should not contain within itself a notion of space and time. Suppose you're trying to understand that why water is wet. Just a rough idea. But don't take it. I mean, just a rough idea just for the sake of illustration. Suppose you're trying to explain why water is wet. Okay. So for this, you break water into the H2O molecules. Then you break it further down into. Water is means our macroscopic level. Then you go down to a deeper level, that is the molecular level, the level of H2O molecules. Then you go down even a deeper level, that is the atomic level. That means hydrogen atoms and oxygen atoms. Now, you are basically all of this you are doing to understand the emergence of wetness in water. But now, suppose if you say that in the atomic level, if you say that a hydrogen atom is wet, or an oxygen atom is wet, and that's why water H2 molecule and water is wet, then it makes no sense. You are trying to explain the emergence of wetness, and you are assuming that at the deep level, at the atomic level, the atom itself is wet. Then who will explain the wetness of the atom, right? So similarly, if you are trying to explain the emergence of space-time from some deeper level, then of course this deeper level should not contain the concept of space and time within it, right? So that's why it's possible that this deeper level has no physical description. Then the only alternative is that it's an entirely mathematical description. That is what we are talking about. So it's likely that underneath the space-time description that we are familiar with, there exists a deeper and entirely mathematical description of the universe with no physical constraints. And yeah, so then if you want to understand what this level is, then it's not clear to me how we can reveal that by studying the physical world around us. The only hope then is mathematics. I mean, of course, I'm not saying that you shut down all the physics laboratories, you shut down work in experimental physics altogether, and you just focus on mathematics. I'm not saying that is not what I'm trying to say. But all I'm saying is that if some theory maybe cannot be verified experimentally, then that does not mean the theory should be discarded, right? Because that's what I want to say in this video. And the last point which I'll make in this video is that the mathematics is probably the future of theoretical physics, which, okay, anyway, we'll get there after 2 or 3 slides. So yeah. Now, but revealing this underlying mathematical structure, assuming it exists, of course, but that would be no easy feat, because we must keep in mind, as I already told you, we must keep in mind that it must not contain any concept of space or time within it, and we must explain how the physical world around us, with its notion of distance and times, or space and time, emerges from this mathematical structure. In particular, I believe explaining the emergence of time would be challenging. See, a mathematical structure is, you can define a mathematical structure in such a way that it, I mean, if you look at the mathematical structure in its entirety, then nothing is changing. If you look at the entire mathematical space or structure, it is not changing. So there is no concept of time in it. If there is no change, then you don't need any concept of time to explain or to understand that system. And when I say mathematical structure or mathematical space, it's not really a structure like for instance, when I say the word structure, what do you think of? Maybe some pattern or something. But a mathematical structure is not a physical structure. I mean, it's not like it's a structure in space, or it's a mathematical space means it's defined using some physical distance. Like here we have a vector of length 2 units. And if I move 4 units to the right, I will have another vector. No, that is a primitive description. But the most fundamental mathematical space, what I'm talking about, it's entirely possible to define mathematical spaces which have no inherent concept of distance and time. So I think that beneath our space-time description, there is such a mathematical description which does not contain any space-time within it. We need to explain how space-time emerges from that structure. But yeah, like this is an illustration. Like a lot of physicists say believe that space-time must be emergent, and with good reason. But so here I think mathematics can directly help physics. Mathematics can play an extremely crucial role in explaining the emergence of space-time, right? And yeah, in particular, I believe explaining the emergence of time would be challenging, because see, everything in the physical world changes with time, but a mathematical space does not change with time in its entirety. So we need to explain how this illusion of change, and hence the illusion of time, emerges when we focus on a part of the whole, or when we focus on a part of the entire mathematical structure, the part which is the physical world. Like I already discussed this, right? And when we move beyond space-time and to the most fundamental level of understanding, then we probably will not find time or space there. I believe whatever we'll find there can best be described in the framework of information, rather than in the framework of concepts like distance and time. I mean, I've discussed information also in some of my previous theories, so in previous videos or articles. I'll not discuss information in details here. I mean, what I mean by information in detail in this video. But yeah, essentially, I'm talking about maybe something along the lines of the John Wheeler's it from bit hypothesis. You can check it out, John Wheeler's it from it. Basically, he's saying that the universe may not have a physical origin. Maybe there is maybe information is the most fundamental level of understanding. Information means it's not any information about distance or time. I mean, there is no concept of space and time inbuilt in information. I mean, that's not what I mean by information here. Okay. Now, I yeah. So a big question here is whether it's possible for the human mind ever to ever achieve such a fundamental level of understanding. Yeah, all of this, I told you my reasoning, my logic, and you say, okay, maybe whatever you're saying is correct. But human mind with all its limitations, will we ever be able to grasp that level of understanding? Will we ever be able to understand this most fundamental mathematical structure? I mean, that's a question I have no answer to, and that's a very valid point. But yeah, for now, all I can say is let's see how far mathematics can take us. Now, here is a second example of how mathematics can help physics, or how mathematics might accelerate the progress in theoretical physics. I mean, this is not entirely unrelated to the first example, that is the emergence of space-time. But yeah, anyway, so it's basically fake problems in physics. Now, as anyone with even the slightest idea of the incompatibility of general relativity and quantum field theory knows only too well, it's possible that we perceive the existence of some phenomenon in the physical world, or some aspect of a theory describing the physical world, which is in violation or which seems to violate some other theory describing some other aspects of the physical world. Like I already told you, like quantum theory, some aspects of quantum field theory violates some aspects of general relativity, but they're successful in their particular domains, in the phenomena they described. So now I think that these problems, which are like the problems in physics, they might be fake problems in physics. Why do I say fake? Because see, I think it could be the case that this apparent problem would vanish if we shift to a more fundamental level of understanding, which can probably be achieved by mathematics. Like mathematics is much more general than physics in the sense that it deals with the space of all objects and structures, which are following certain mathematical relations between them, and it does not exclude any possibility. Physics, on the other hand, is only concerned about those possibilities that occur in our physical world. So this means by studying physics, we are only considering we can only see a part of the whole, and the problems that arise when studying physics or when studying just this part, they might be automatically resolved. I mean, they might kind of vanish if we look at the whole, and that is the mathematical description, the most fundamental mathematical level of understanding. Like let me give you a simple illustration of what I mean. Like okay, here I've given this illustration about thermodynamics. An even more simple illustration could be suppose a car collides with a wall. So even a high school student knows that energy is always conserved. So when the car was moving, the car had some kinetic energy, but then the car collides with the wall and the car comes to a complete stop. So the kinetic energy of the car drops to zero because the velocity of the car drops to zero. Now, if you are looking only at the part, that means if you are looking only at the car, then it seems like the energy of the car was initially non-zero. It had some kinetic energy, but then the energy suddenly drops to zero. So the energy kind of vanishes. Then in law of conservation of energy does not hold. A law of conservation of energy is violated. I mean, that is what will be your premature conclusion. If you only look at the car, that means if you only look at the part, but if you look at the entire system, that means the car as well as the wall, then you will see that the once the car collides with the wall, maybe the wall breaks, or maybe there is some noise, there is some and maybe the wall disintegrates, the car disintegrates. So if you study the entire system, if you look at the whole system, then you can see that the law of conservation of energy is not really violated. Rather, the kinetic energy of the car is being converted into different forms of energy. Maybe sound energy, the noise on the collision, maybe the energy that was required to break the wall, to disintegrate the wall, and all of this. So the same approach, like here a simple illustration could be the fact that open systems like living organisms, open systems means systems that exchange information, or kind of exchange matter with its surroundings. Like we humans, living organisms, we are open systems because we breathe in the air from the surroundings, we exhale some air, we exchange matter with the surroundings, right? So we are open systems. and open systems decrease entropy locally. I mean, this is just basic knowledge. You might know that entropy is a measure of disorder. I mean, that's not exactly true. Technically, entropy is, if you consider the information concept of entropy and all entropy, the Boltzmann definition, entropy is not as simple as a measure of disorder. It's something more than that. But yeah, roughly speaking, entropy, I mean, more the disorder, more the entropy. And more mathematically, more the number of ways you can achieve a particular state, higher the entropy of that state. But that is the technical definition. I mean, in simple terms, more the disorder, more the entropy. But living organisms within themselves, they maintain certain order, at least for as long as they're alive. I mean, for say for a few years, living organisms, they maintain a perfect order, and so it might and in fact they decrease entropy locally. So if you do not take the surroundings into account, that means the whole, and if you focus just on the part of the whole, that is if you focus just on the living organisms or just on the system, then it may seem that the entropy is decreasing and the second law of thermodynamics is violated. The second law of thermodynamics says that the entropy always increases. Entropy of any isolated system always increases, and in case of open systems, the entropy of the total system plus surrounding must increase. But if you look only at the system, then it might seem like the entropy, this second law of thermodynamics is violated. However, the overall entropy of the universe, as we know, always increases. So we all know all of this, like this conservation of energy, second law of thermodynamics. But this was just to give an illustration. Now, although it's not yet clear how to use this reasoning, this line of reasoning, or how to use this approach to solve the problems that arise when we attempt to reconcile gravity with quantum theory, but I think the same approach coupled with some good mathematics might do the trick. Now, of course, you might say that we already know all of these examples you are giving, but yeah, the point of these illustrations, the second law of thermodynamics and the conservation of energy, these two illustrations, I mean, that was the point to illustrate the idea. Of course, we do not yet know how to resolve the issues that arise when we attempt to kind of merge gravity with quantum theory. But I think this same using the same approach, if we try to kind of zoom out and go to a more fundamental level of understanding, that's the mathematical level, then maybe these problems will disappear, and then we will say that, oh, this was actually a fake problem. Like today we think that if somebody told you that, come on, I've discovered a problem with physics, and that is that living organisms violate the second law of thermodynamics, then if you are well educated in physics, you will identify that it's a fake problem, because it's not really a problem at all. This fake problem or this illusion of the problem, it arises only because you are not taking the entire system plus surroundings into account, right? So similarly, that is what I meant. So this is a second example of how mathematics might accelerate the progress in theoretical physics. So basically what I'm trying to say is that right now in theoretical physics, we are confronted by this kind of this barrier that we cannot formulate a unified theory. We cannot unify the theories of gravity with the theory of quantum theory, with the theory of quantum mechanics, quantum field theory. Now, I think that the conventional approach that trying to formulate better experiments to explain this and all these things, maybe that approach is not going to work any longer. Maybe we need to follow a different approach, maybe the approach I outlined in this video, that maybe we should look for some more fundamental mathematical description of reality beyond space-time, and maybe then automatically these issues will be resolved. That's what I'm trying to say. So let me now I've come to the last slide, and that is mathematics, the future of physics. So when I started this video, it was mathematics, the future of physics. There was a question mark. At that point, I was asking, like, is the future of physics mathematics? Now, since it's the last slide, so it's time for me to give a verdict. And according to me, of course, it's just my speculation, my opinion. I'm not saying that this is correct. But I think that mathematics is the future of physics. That's why I've removed the question mark from the title of this slide. The key to unlocking the secrets of the universe might not lie in devising better experiments and formulating theories based on the results of these experiments. Like I said, this approach has been remarkably successful in the past, but that was the past. I think the future of physics belongs to mathematics, the only place where truth and beauty mean the same. This last portion is actually there was a famous saying that mathematics is the only place where truth and beauty mean the same, and to be able to appreciate this saying, you need to understand what do we mean by beauty here and what do we mean by truth here, because mathematics is the most fundamental level of understanding we have. It's the purest form of human thought. That means it's kind of truth. And mathematics is beautiful in the sense that, by beauty I mean elegance of a mathematical theory, rigidity of a theory. I mean, when you say a theory is beautiful, you mean the theory is mathematically elegant. I mean, the theory has very little or no assumptions, and the theory is that is what do you mean by beautiful theory? Beautiful theory doesn't mean a theory which is very easy to understand, which looks the equations look beautiful or something. It's not a beautiful person. It's a beautiful theory, right? So by beauty here, I'm talking about elegance, the less number of assumptions. The theory should be derivable from first principles, and that is what I mean by beautiful theory. So mathematics, and most mathematical theories satisfy these conditions, and that's why it's a famous saying that the mathematics is the only place where truth and beauty mean the same. So anyway, guys, that was all I wanted to discuss in this video. And again, like I said in the beginning, also comments and constructive criticisms are welcome. It's a pretty fundamental question which I've tried to address in this video. Of course, my answer is speculative and vague, right? But the question is a deep question, and of course, to be able to answer this question, we need to work hard, and maybe the answer will reveal itself in the next 100 years, next 200 years, or I don't know whether it will ever reveal itself. But yeah, that was all for this video, guys. I would love to know your thoughts on this. So let me end the recording here. Thank you very much.